Thank you, everyone. Thanks for coming. And today we have Benjamin from Yale. He's a postdoc at Yale, and he will talk about this BAO cosmology with HIRAX radio telescope. Let's just welcome our speaker, and we can start.
All right. Well, thank you for having me to give a seminar. I'm sorry I couldn't make it out there in person, but maybe when travel is back on the menu, I can stop by to see you guys. But yeah, so I'd like to talk about the HIRAX telescope, and I'll give a brief introduction to Baryon acoustic oscillations in case there's students or people who are unfamiliar in the audience, and then I'll talk a bit about the HIRAX array design and the scientific forecasts, the purposes for which it was built or will be built, and then talk a little bit about what we're doing right now at Yale and throughout the world on developing the experiment. So 21 centimeters is a phrase that you probably hear a lot right now. So the 21 centimeter line is the hyperfine or spin flip transition line in neutral hydrogen. So this comes from if you have the spin of the proton and electron aligned in hydrogen, it has slightly higher energy state than when they're anti-aligned. And the transition from that aligned to anti-aligned state corresponds to an emission of 21 centimeters wavelength, or 1.4 gigahertz. And this is really useful as a astrophysical and cosmological probe for a number of reasons. Kind of the first of which is that it's a classically forbidden transition. So the lifetime of the excited state is very long, on the order of 10 megayears. And what that does is it makes the emission line very thin in frequency. So you kind of get for free, along with your measurement of the intensity of this line, you get a determination of its redshift, of its distance. And that's, we hope will allow us to build up these large tomographic three-dimensional maps of the emissions without having to do follow-up spectroscopic or redshift surveys as you would with other tracers of structure. The long lifetime also means that the spin temperature decouples from the kinematic temperature, so you can get a measurement of the ionization fraction at the time, which is less comes into what I'll be talking about. But if you're for a number of experiments that are doing things in like the reionization epoch, knowing how much of the intergalactic medium is ionized at the time is very crucial for them. So you're getting kind of multiple measurements all at once. Line. And then it's very interesting cosmologically because hydrogen is incredibly abundant in the universe, right? It's everywhere and is unionized for large chunks of the universe's history. And it's very isolated from other lines. So kind of unlike a lot of other spectroscopic lines that people look at, there's much less confusion. So it's very clear what the redshift of the emission is, so it's easy to determine. And then because it's a tracer of structure of the Baryon acoustic oscillations, you can use it as a standard ruler to map out the expansion of the universe over time and to get a handle on parameters like dark energy and dark matter. So then what are Baryon acoustic oscillations? So before the time of the CMB in the primordial universe, in the primordial plasma, you have oscillations that are set up where gravity wants to compress over densities, and the photon pressure provides a restoring force. And then from like first year physics, anytime you have these two opposing forces, you get oscillations. So these are actually acoustic. They're actually sound waves in this plasma, and they propagate until the time of the CMB, when the photon pressure decouples, and then the sound waves just freeze in at that scale. And so you get this characteristic power spectrum of oscillations and kind of the largest length scale called the sound horizon at about 150 megaparsecs. And then once you have this frozen in density structure, further structure growth tends to preferentially happen at the overdense places. So things want to collapse more towards there. So you should see a distinct correlation pattern in the location of structure on large scales. And this has actually already been seen for quite a while. We've been doing this in the optical, looking at spectroscopic redshift surveys. So I have a plot here from the SDSS survey and the corresponding power spectrum. And so this wave in the power spectrum there is exactly what you expect from these acoustic oscillations. But what kind of the thinking is with 21 centimeters, that doing this is kind of wasteful in a way. In each of these kind of characteristic BAO structures, these like rings, there's of order 10 to the 5 galaxies. And so when you're trying to map out this large scale structure by pinpointing each one of those individual galaxies, you're ridiculously oversampling things. You don't need all of that resolution. So the idea is, with 21 centimeter, you're tracing out the neutral hydrogen that correlates with the optical galaxies as well, but it has kind of a naturally larger structure to it. So you can have instruments with very large angular resolution and map out more volume of space more quickly, because what you're after is really the statistics on the behavior on large scales. So then you're like, oh, you could say, okay, well, if this is such a better way of doing large scale structure surveys, why hasn't this been done before? And the answer is the signal is incredibly low amplitude. So the intensity of the 21 centimeter line signal should be on the order of 0.1 millikelvin. And the primary foreground is the Milky Way galaxy with synchrotron radiation. And it's sitting there blazing away at 10 to the 5 Kelvin, 6 orders of magnitude higher than the signal we're looking at. And so that drives us to the necessity of building very large instruments. So we're building these large arrays of hundreds or 1,000 dishes, and that's a little bit difficult. We're also then driven to operating in interferometric mode, and that's really what's prevented this from being done 20 years ago or something, is we didn't have the processing power to be able to do the correlations between 1,000 different dishes. But we were getting to the point now where that is technically feasible, and that's why there's a lot of these instruments kind of in development or coming online. We know that the signal is actually there. It's been detected in cross-correlation. So this was the first cross-correlation detection by Suqing Chang et al. Between GBT measurements of H1 and the Deep2 optical survey. So we're confident that the signal is actually there. We just have to build an instrument that's sensitive to see it. So then what is HIRAX? So HIRAX is the experiment that I'm working on. It nominally stands for the Hydrogen Intensity in Real-Time Analysis Experiment, but really it's just an excuse to have this fuzzy little creature as our mascot, which is HIRAX with a Y. They're little burrowing mammals that live in South Africa, and they're neighbors of the meerkats. And our telescope will be a neighbor of the meerkat telescope. So there's kind of a tradition of naming instruments after the local fauna in South Africa. So HIRAX is a collaboration that's actually led by South Africa, and at the moment funded completely through the South African NRF, kind of their equivalent of the NSF in the US, although we're looking into funding from the United States and elsewhere. But it's a collaboration between universities in South Africa and then a number of institutions in Canada and in the United States. And then the map is to show where things are located if you're not familiar with South Africa. So Durban on the Indian Ocean side on the East Coast is where the lead institution is based. And then at Johannesburg, we have a prototype array that I'll mention a little bit. And then the mark in the middle of nowhere is where the actual final array will be. It will be at the square kilometer array site in the Karoo Desert in South Africa. So there's actually a large radio astronomy preserve that's been set up there, where we'll be constructing our array. So the design of the array is it'll be a close packed array of approximately 1,000 6-meter diameter dishes, operating between frequency of 400 and 800 megahertz, which corresponds to 0.8 to 2.5 in redshift. And the idea is to operate in drift scan. So you're building 1,000 of these dishes. We want to keep them kind of cheap. So they're not electronically steerable. They have no motors on them. So you just point them all at one direction in the sky, and you let the Earth spin and let the sky scan overhead. And then every half a year or so, you repoint and map out a new stripe on the sky, and build up a survey of much of the southern sky over the nominal 4 or 5 year survey. The primary science goal, as I talked a lot about, is measuring the Baryon acoustic oscillations. But anytime you have a large survey that's just deep and covering a large chunk of sky, there's lots of other stuff you can do with it. And for us, some of the other things that we're looking at is looking at discovering or monitoring radio transients. So you can do pulsar timing, and we can also detect FRBs, fast radio bursts, which have been in the news a lot recently. And I'll mention a little bit more about them later on. And we can also look at neutral hydrogen absorbers. And I mentioned that the worst foreground for us is the Milky Way. But kind of a positive spin on that is HIRAX will have some of the best maps of the Milky Way at these frequencies by the time we're done. So for people who are interested in local astrophysics and not the cosmological stuff, those maps will actually have data. They'll have useful information in them. So we have this very wide bandwidth of 400 to 800 megahertz, so we can get a large chunk of redshift. So that's driven our design for the antennas. We have these cloverleaf dual polarization antennas with very low loss and low reflectivity across our band. They're made of FR4, just circuit board material with a metallized layer to keep the cost down. And they have this kind of ring choke, it's not actually a choke, this ring can structure behind them to help circularize the beam. Because the array is rather large, we're using fiber optics to carry the signals to the correlator from the dishes instead of just coaxial cable, because the losses in coax and the number of other features like temperature dependence of the transmission are significant. So this has pushed us to have the majority of our amplification on the dish, on the antenna. So we have a 50 dB low noise amplifier in the balun, in the stem of the antenna, and then the rest of the amplification at the correlator on the other side of the RF over fiber. But this is just because the RF over fiber transmitters are a very new technology and are still relatively noisy. So we want the system noise to be dominated by the LNA and not the noise from the fiber transmitter.
Sorry, what's on the fiber? Is that an analog signal then, or a digital signal?
It's analog. Yeah.
Analog, yeah.
Yeah. So what's going on is you're taking the radio frequency signal at the antenna and you're modulating it into an optical signal on the fiber optics, and then it's demodulated back down to RF frequencies at the correlator. But it's completely analog all the way to the correlator. Yeah.
So you're saying such a device is actually what sort of dynamic range? I mean, actually, you did mention you're going to need pretty large dynamic range, but that's the challenge, I assume, because under normal circumstances, I wouldn't have thought it was. I would have thought you could get a decent signal to noise on such a system, but it's the huge dynamic range that you need that is the challenge, is it, in terms of the signal to noise?
So it's my understanding that it's not the dynamic range, but it's that the step where you're modulating the RF into optical so that you can transmit it on laser, that's just noisy. This is something that's been developed kind of in the field. A lot of the other technology on these radio telescopes are just kind of hijacked from like the commercial world, because they've developed wonderful amplifiers and things for cell phones and everything else. But this is not something that's been developed elsewhere. So it's very new. So that it's possible that will become less noisy in the future, but it is not right now.
And are you using linear? Do you know if is it linear amplifiers, or using logarithmic or anything like that to help with this range issue and other things? How sort of sophisticated is the analog signal processing before it goes into the modulator?
Yeah, I believe it's a linear amplifier, but right. I'm not entirely sure on that. Kevin Bandura at Western Virginia is the one who's who's developed the LNAs for the system.
Right. Right. Thank you.
Okay. Yeah, and then yeah, if anyone else has questions, yeah, just jump in during this. That's fine with me. Yeah. So then the back end of the system is kind of analogous to the system on CHIME, and this is kind of becoming a standard kind of architecture for interferometers. This kind of FX architecture, where there's two different computational engines. There's the F engine, which in our case is built on ice boards developed by Matt Dobbs at the University of McGill. And this is doing the digitization and the channelization, and then what's called the corner turn operation. So the way the data comes in from the dishes is all of the frequency bands from each dish, but the way that the correlator wants to see the data is the data from all of the dishes, but at a single band. So you have to kind of split out the frequencies and then recombine them into the format that the correlator wants. And then the correlator, the X engine, is built on GPU architecture, and this is being developed by Keith Vanderland and his people at the University of Toronto. And then some very brief, rough forecasts for an instrument which doesn't exist yet. So there's lots of caveats in all of this. But if things go to plan with kind of nominal survey length and area, we should be able to measure the power spectrum of the Baryon acoustic oscillations out to the 4th or 5th peak. So the plot on the left is for the full array, the 1024 array, and then for a kind of a step in the build out at 128. Because this is a very modular array, we can operate during the build out, and we'll be collecting data that whole time. And so it will take a while before there's sufficient sensitivity to get cosmological data, but we'll be able to do some interesting science before we have the full array kind of in action. And then the plot on the right is showing a comparison to kind of current generation optical BAO surveys. So you can see that we'll have comparable or better kind of error bars, but then the main kind of advantage is pushing out to a new redshift regime that hasn't been explored yet. This redshift range is kind of comparable to next generation optical surveys like DESI, which will be kind of operational on similar timescales, and I believe we'll have kind of similar error bars, although we haven't done that comparison thoroughly yet. The interesting thing to kind of note there is that this really isn't in competition with a survey like DESI or EBOS or something, because it's a different tracer. So they're looking at the optical galaxy signature, and there's an optical galaxy bias going from that tracer to the underlying dark matter distribution. Whereas with the 21 centimeter, you have a different set of biases going from the H1 to the underlying dark matter. So there's a lot of work that can actually be done kind of in cross correlation between these data sets once they exist. And then again, very preliminary kind of matrix plots here of the cosmological parameter constraints at the end of the day, and the kind of the things that we expect to have the largest improvements on are the things you would expect from a large-scale structure kind of survey. So it's sigma 8 and H naught and omega dark energy. And then a little bit about one of the main secondary science goals that the people are excited about. So within the last few years, there's been a lot of interest in these recently detected fast radio bursts. So these are short, kind of millisecond duration Jansky brightness bursts that we believe are cosmological in distance due to the dispersion measure, and also there have been a couple now which have been localized and tentatively assigned locations at cosmological distances, not within the Milky Way or in local galaxies. only a very few of these events have been seen to date, and their origins are completely mysterious. So if they are cosmological distances, then they're extremely bright, which kind of leads people to believe that they're some kind of cataclysmic event. But then there have been a couple that are repeaters. They're not regular, repeated pulses like with a pulsar, but they're the same object flashing multiple times, which kind of would seem to rule out a cataclysmic event. So it's not clear yet what they are, or if there are multiple populations. Maybe some of them are cataclysmics and some of them are something else. HIRAX and kind of our sister experiment in the Northern Hemisphere, CHIME, are hopefully going to shed a lot of light on this, because the limitation is just having enough beams, enough area, on the sky to detect them, because the total event rate is expected to be quite large. And CHIME is actually has some publications now on FRBs detected with their Pathfinder array, and they are in fact seeing large numbers of these events. So we're excited to bring this from a study of a few dozens of individual events to a large statistical study of these objects in the next few years. So then where we stand right now is that there's a 10-element array at the Hartebeesthoek Radio Astronomy Observatory in South Africa near Johannesburg, where they have a little bit more infrastructure than they will way out in the Karoo. So we're doing some of our initial testing there. So we're currently testing our f.5 dishes, 0.25 dishes. So these are very deep in an attempt to decouple the dishes from their adjacent dishes in the array, because it's close packed. And we're also testing the RF over fiber hardware, and just getting a handle on data analysis and techniques as well. This array will not just be shut down once the full array comes online. It actually will continue to be operated as an outrigger. And we're also looking into building several other outrigger stations throughout southern Africa, so outside of South Africa, but into Namibia and Botswana and kind of the locations to the north, to improve the angular resolution of FRBs. So one of the things that we hope to do is to be able to not just detect, but to localize them to their host galaxies with our own internal array. So then kind of the work that's going on right now. So one of the things that I've been working on a lot is doing the mechanical and electromagnetic simulations for the dishes. And we have a tender going out for the final dish production in the next month or so. And you can see in the previous slide, the feeds are, in the current model, are held up with these like feed legs that come in from the outside of the dish. But we've discovered that induces some polarization structure into the beams that's actually noticeable according to the simulations. So we'll be moving towards these fiberglass feed columns, which I've done some work simulating, which should be easier to build into position, and also significantly stronger than the feed legs. And then there's a lot of work going on still with optimizing the dimensions of the structure, the feed and the can, and a lot of this work is being done by myself and also by Aaron Newell-Weiss, who's a postdoc out at Caltech. And this is motivated, like I mentioned, the move away from feed legs and several other changes in the system. There's also a lot of kind of cosmological simulation work being done, mainly in South Africa, being led by Devin Crichton, a postdoc down there, where he's using the Shaw M-mode formalism to produce synthetic visibilities, and we're working on tying his cosmological simulations into the E&M simulations, so that we can take realistic beam models from the electromagnetic sims and propagate them into cosmology to look at how deformations of the dish from wind or gravity or imperfections in the manufacture of the dish or in the feed location propagate into uncertainties in the cosmology, to help generate specifications for how accurately we need the dish is manufactured and how accurately we need the feeds positioned for the dish tender and then production. At Yale, there's also a lot of work going on in feed simulations and then kind of verification measurements. So a lot of this work is being done by Emily Kuhn, who's a grad student that I work with. And she's developed this cryogenic test bed for measuring the noise temperature of our feeds using a differential measurement. So you're looking at the difference between the power received looking at a hot load and then a liquid nitrogen cooled cold load. And using that to work out the noise temperature of the feed itself. This is analogous to what's done in like CMB for the measuring the properties of their detectors. The difference here is that the beams of our antennae are very large. They're basically a full hemisphere to fill our very large f over our f number 0.25 dishes. So capturing all of that that radiation is and putting it onto a cold load is tricky. So Emily's done a lot of work designing these very large cryogenic tanks that are about 5.5 feet in diameter and have this RF absorbing foam with these large blue pyramids that you can see in the picture on the right to capture that load. And these are built and constructed and operational now. And we did some preliminary noise temperature measurements with them before our lab shut down in March. So this is ready and waiting, sitting in the high bay at Yale for us to start running through measurements of the feeds as they're produced. Another kind of activity that's going on is doing range measurements of the beam patterns of the feeds. So this is without the dish, but just the feed itself. So we've done a couple different kind of measurement campaigns at JPL's Mesa facility, and then more recently, Emily took measurements at North Carolina's indoor range. So these are pictures from the range in Pasadena with one of our cloverleaf antennas on the left, and then our drone calibrator on the right, which I'll be discussing a bit more later. We're running a little short on time, so I'll skim through some results here. So these are from the outdoor range measurements at JPL. Measurements of the CHIME feeds, which are very closely related to the HIRAX ones that have the same kind of cloverleaf structure. And then comparing them to simulations, and this was very promising. This was the first time that there had actually been real measurements of the feeds on any range. So we were quite pleased with the level of agreement there was with the simulations. There were some noticeable discrepancies. In the top right plot, the widening of the top of the beam is because of this large ground plane that there is behind the feed that you can see in the photo on the left, the previous slide. And we were also predicting that the kind of shelf structure in the orange line in the measurements on the sides was also due to the range. But modulo those kind of range effects, the agreement was quite good. But this also led us to be very interested in doing something in a more sensitive indoor facility where you wouldn't have those reflection issues. And then in February, Emily went to NC State to conduct those measurements, which I have in a couple slides. There's also an interesting kind of side note if you're doing drone calibration, like the folks on TNLI. So Greg, you might be interested in this. Our drone calibration system I'll show more later, but we're using a biconical antenna suspended below this DJI Matrice drone, and we found that the antenna actually couples very strongly to the drone, which is made out of carbon fiber, which turns out to be a very, very good radio reflector. And so we discovered at JPL that if you just have the antenna strapped to the drone, that's the blue curve, and it looks horrible. But you can decouple them quite effectively by just throwing a metal plate, a ground plane, in between the two of them. And we're doing some. Emily's working on some simulations now to explore how to better.
When you call it a ground plane, when it's hanging off a cockpit?
Yeah, yeah, maybe that's not the right word. But it's a decoupling plane. It shields you from so the back lobe of the antenna is just reflected off of something flat and doesn't see all the complicated structure of the drone.
Oh, I see. Okay, so the artifact is because of the complicated structure of the drone. So
Yes.
You're saying it's a simplification of the source.
Yes.
I see. Gotcha.
Yeah. Because you've got. I'll show the drone later, but you've got this, like, it's got 6 legs, so you've got this hexagonal pattern coming off, and then the body of the drone is also not entirely symmetric, and it's just there's like landing gear. It's just really ugly and complicated. Yeah.
Got it.
I have another question,
Yes.
slightly unrelated to the plots that you're showing currently, but if I want to understand as a non-experimentalist the difference between HIRAX and CHIME, I mean, besides the fact that they're in different hemispheres, what should I be looking at? The observable, etc. Yeah.
So I have, if we have time at the end, I have a backup slide on some of the differences between the two arrays. But in science goals, they're the same. So we're measuring the same redshifts, and so the same structure in the universe. The idea is that because they're in opposite hemispheres, they're complementary. So you could imagine eventually combining the data sets from both to improve your statistics. The main difference between them is in the front end architecture. So CHIME uses these long cylindrical kind of half pipe looking antennas, which were designed to just be easy to have a large collection area. The problem that they're running into with that is that it's very hard to calibrate, because the antennas then are all in a line down this half pipe, and so they're all coupled to each other, and you get a lot of crosstalk between them. And it's very hard to simulate as well because of the difference in scales between the small antennas and the huge reflector. So it's also very hard to predict what your beams should look like with good accuracy. So that's pushed HIRAX to using these deep parabolic dishes. But the difficulty of calibration is like one of the main challenges with these kind of arrays. And that leads to the last thing that I have to discuss, which is the drone calibration of the array.
Thanks.
Yeah, so there were these JPL measurements which were promising, and showed up a lot of interesting structure that we hadn't expected, but it also showed some range effects. Emily did some work more recently, right before things shut down again, at NC State, and got these measurements of the HIRAX feed and CAN, which are much cleaner than the JPL ones, and kind of further validate our trust in the simulated beams that I've been producing. So we have E and H plane cuts. Yeah. So the last thing I discussed is calibration, which is always a challenge with telescopes, but particularly with these large arrays, for a number of reasons. Kind of largely because they're operating in drift scan. So you can't just point your telescope at your favorite source on the sky, or at an artificial source on the ground and just scan back and forth over it to map out your beam. You're limited in you're just pointing in one direction, and it's very difficult to scan. So the solution that we and other people have been developing is to, if you can't scan the dish, then scan the source. So you just kind of invert the problem. And you strap your radio source and antenna to a drone and fly around over the dish, which seems like it's a simple solution, but in reality there's a lot of complications that make this much more challenging. So this is the Yale drone calibration system with the lab dog as our mascot. and for scale, one standard dog for scale. This is a drone from a company called DJI in China. This is their Matrice 600 Pro drone. It's quite large. It's got a wingspan of five or so feet, and it's 2.5 kind of feet tall. So this is some of what I just said. So this is the DJI drone, and we're kind of enabled here by the fact that the near field, the far field for HIRAX is quite close. So it's between 1 and 200 meters, depending on the frequency. So the drone can easily achieve the far field, and then it's quite simple to mathematically to do the measurements there. And we've actually done our first measurements with this at the DSA-10 array at Overo out in California, and then some measurements in March at the BMX telescope at Brookhaven, which I'll show data from. The source that we're using is a homebrew. So this was developed by Yale, by Laura, and an electrical engineer here, Thomas Barker. This calibration platform is designed to be used for a number of different experiments. So for HIRAX and CHIME, which are the same frequency band, but then potentially also for other instruments such as DSA and BMX, which I mentioned, which are similar 21 centimeter frequency ranges, but different band. And then the antenna that we're using is this biconical antenna from a company called Aronia in Germany. So then some of the things that make this difficult is that you need very high positional accuracy to actually get a good picture of your beams. So you don't necessarily need to be able to command your drone to these precisions, but you need to know where it is. So that you can reconstruct the map. And the kind of the specification that we have for CHIME is slightly less stringent for HIRAX, but it's less than 2 millimeters is kind of the accuracy that we're shooting for. And then similarly, kind of pristine measurements in the various kind of like rotational angles of the drone of below a degree. And then there's some kind of ancillary problems with actually recovering the data, this positional data from the drone. These drones were not designed for physicists who want to know things to double float precision. They were designed for photographers or filmographers, right, who don't actually care where their drone is. They might want it to be very stable, but they don't necessarily need to know the positional data to read out. So actually just getting the data out of the drone has been a little bit challenging. And then there's always like a syncing up kind of challenge of matching your data from the drone to what you're actually seeing in the telescope. So verifying the accuracy is something this is actually work being done by a couple of undergrads in our group, by Annie Polish and Miley Harris. And we believe that we've, with a differential GPS system, we've tied down the relative precision of the drone's location to better than a centimeter. So to within the spec that we need. So this was us out at Overo in the bottom picture there, positioning the drone over a USGS survey marker, whose position is known to about 1 millimeter, and then just recording the position of the drone for a long period of time and like rotating it and shifting it around to see that we can actually reconstruct its position. And this is done with a differential system. So the idea here is that you've got a ground station, which is pictured on that tripod, whose location doesn't move, and then there's the drone that does move around. And so when there are errors in the GPS signal that come largely from the satellite ephemeresis, and so if you know that these two receivers are seeing the same errors, but one of them is not moving, then you can do a differential measurement to reconstruct the position of the drone to much higher accuracy. And this is just a scatter plot of the drone sitting stationary on that survey marker, showing that we can measure the position very accurately. Getting the absolute position is actually a slightly different matter, and that requires you to use more information about the satellite ephemeresis. And that is still a work in progress. But the precision, at least, the kind of relative accuracy is within spec.
Could I ask you a quick question?
Yeah.
I'm not sure, at these frequencies, how far away does the drone have to be for it to be in the far field of the dish?
Yeah, so for HIRAX, that's 1 to 200 meters. So that's easily achievable with this drone. For CHIME, the far field is much higher. It's like kilometers. So for the CHIME beam mapping, we will not be operating in the far field. We'll be in the near field, and there'll be a near to far field transform that you have to perform on the data. And one of our grad students, Will Tyndall, is currently working on that part of the software side of the analysis.
Okay, that's interesting.
Yeah, well, here he is, in fact, actually. So this is Will Tyndall. So another thing that you worry about with drone used for this calibration purpose is that your drone is also putting out RFI, and a lot of other groups have been having trouble with the noise from the drone being comparable to the kind of the amplitude of the signal you're transmitting. So we've been doing some measurements and verification there. So far, it looks like this model from DJI is very good RFI wise. It's significantly quieter than the source that we're using, so we think we should be safe there. We're not quite sure why that is. One theory is the brushless motors are just put out a lot less static than kind of cheaper motors, but that is another concern that kind of is always has to be in your mind here. So this is our first actual beam map from a drone. So we flew this kind of cross pattern over the DSA-10 dish at Ovro, and measured the beam pattern as a function of frequency here, and get that it comes out to be consistent with the design of the dish at Ovro. So we were very, very pleased with that. This was flying manually, actually. We didn't have a functioning autopilot yet. So ideally, the plan is to not just do this kind of cross-shaped pattern, but to fill out with a grid, so you get a better picture of the beam. And that was what we did at Brookhaven a little bit later. So this is another 21 centimeter experiment that Andrzej Slosar is developing there. It's mostly used for prototyping hardware, but he's also hoping to do some kind of local Milky Way and neighboring galaxies kind of science with this. And it's these 4 off-axis paraboloid dishes, and it's tuned for the rest frame 21 centimeter line, so 1.1 to 1.5 gigahertz. And so we flew there in March, and by then we had a nice autopilot software set up, so we were able to fly these dense 2D grids over the dish, and fit 1 and 2-dimensional parabolas, and we're starting to get to the point where we can see side lobes in the dishes, which is one of the major goals. So you can even kind of see those here. These are the 4 different dishes, and you can even kind of see that they're in 4 different locations, although there's a little bit of a pointing error in one of them. And you can actually see the blob kind of north and south of the main lobe of the beam pattern. There are the side lobes. And so then this is some work by people at Brookhaven doing 2-dimensional Gaussian fitting to that. And so you can see that we recover the beams really nicely, and it agrees with what their modeling says it should be. But there are some interesting features as well that were not predicted that we're kind of picking out. You can see that there's a kind of so the asymmetry in the beam pattern is expected because of the shape of the dish. But the fact that it's rotating slightly as you change in frequency is a new feature, I think, that we discovered. We can also look at the full width half max as a function of frequency. So this is the data for all 4 of the dishes kind of across frequencies, and you can see that it, I'm flipping back and forth here, it scales according to the Rayleigh criteria, like you would expect, at the 1.22 lambda. And there's a filter that cuts in at 1.5, so that's why it goes nuts after that. So we can verify the kind of the spectral structure of the beam as well. And then we're starting to see side lobes. So this is many different passes over one of the dishes, but kind of all co-plotted. And from the null and the kind of, modeling this as an area disk, measuring the width based off the null, again, like you can pull out the diameter, the size of the dish, and it comes out correctly. So this is kind of as expected. Although there's one caveat here that this data might be slightly compressed, so that the side lobes may actually be at a lower amplitude than they appear to be here. And then just a very quick, very preliminary comparison to kind of other drone beam mapping published data from Tianlai and the Blind Observatory, shows that we're very happy with this because we're starting to get into the regime where we can actually say something about the beam and about its side lobes and spectral structure, and so this is kind of approaching data that we'll be interested in actually publishing sometime soon. But great strides have been made. So that's kind of where we stand now. The next couple kind of steps are taking this drone calibration system to either we have some HIRAX prototype dishes at the DRAO in Canada, or down to South Africa once we have dishes up there as well, and that's just all kind of waiting on the global situation. And then we're also, as I said, putting out a tender for the production of the dishes in the next month or so, and that preliminary stage is going through. It looks like we will have bidding on the dishes, but then when the construction can actually start, again, depends on just the global climate. But that's kind of the next stage is start building stuff and start measuring it in the field. So that's where we are. Does anyone have any questions?
Very good, thank you.
I have a question, but this is like slightly far back. So when you showed the projections of HIRAX 128 and 1024 for the BAO, I mean, there's the K, I mean, the wave number 0.1 megaparsecond versus where like your sensitivity, so in terms of the error bars, is the highest. So I'm wondering if like you tuned your experiment to such that this is a window in which it was like optimal performance and then it sort of tuned away outside, or is this, I mean, I'm wondering where the varying size of the error bars comes from. I mean, I think if you go to the slide, it'll,
yeah,
I might be able to hand wave slightly more concretely.
To look at the plots. So this kind of this one.
Yeah, exactly. So you see, there's a window around the natural BAO scale where your error bars are excellent, and then it sort of falls off. So I'm interested in the small wave number. Like, why do the error bars get worse? Is this something that you tune experimentally, or is this just because there's no data?
Yeah. So both. So on it's different things on either end.
Okay.
So the experiment is tuned to be sensitive at the BAO scale, which is kind of on the order of 3 degrees. It's like 0.3 to 3 degrees depending on the redshift at these redshifts. And then on the one side it's because you don't have the sensitivity to see things that are smaller, and then on the other side you're getting to things that are are very large on the sky, and so there are just fewer of them, right? So that it's the cosmic variance limit on the other side.
I see.
Kind of the two things that are bracketing you is, yeah, instrument resolution and then cosmic variance.
Right. So instrument resolution on the small scales and cosmic variance on the large.
Yeah.
So how, if you want to extend such a study to smaller scales, you would just have to like make a different instrument, like effectively.
Yeah, you would need something that has finer resolution, and this was kind of deliberately designed to have this large beam on the sky so that you can it speeds up your what you call your mapping speed, so that we can map more of the sky in a fixed amount of time. Yeah, so it's optimized to get as much of the sky as possible for this specific length scales. Yeah, so if you're interested in smaller scale structure, then you need a different instrument with larger dishes, and probably something that you can actually steer if you want to like point at specific objects on the sky.
Right.
There are lots of things that do that, right? ALMA is much more like that, where they're looking at kind of similar frequencies but small scale structure. Yeah, so the benefit of this instrument is that it's going after the large scale stuff.
Interesting. Thank you.
I have a question or two, if you don't mind.
Sure.
Specifically, do you need to do imaging to extract BAO power spectra from 21 centimeter data?
Yeah, we do not. And in fact, this experiment is not intended to actually image. Yeah. So we'll be looking at just at the power spectrum and extracting the cosmological parameters from that.
Gotcha.
It's actually much trickier to do imaging. So the array design becomes much more important then. Our array design is just a close packed square grid, and that is ideal for getting the sensitivity at these wavelengths or wave numbers, but it's not ideal for imaging. Both having it close packed and having just basically like two axes of redundancy, you get very poor images from that. So if you were interested in imaging, you would want a kind of hybrid array that had a dense core, but then also had elements spread out much farther, and they were much more randomly placed, so that you fill out the UV space better.
Sure.
So HERA is another 21 centimeter experiment. They're trying to do imaging. They're not completely random, but they're more diffuse, and they're in a hexagonal grid that's actually like offset into 3 chunks, so that there's different baselines between the 3 different sections to try and improve their imaging capability. To do it like really, really well, you would want something like the square kilometer array, where you've got really randomized locations and on very different length scales. Yeah.
Sure. And I had one more question as well regarding the beam mapping that you've done. If you want to jump back to the end, you had some plots showing cuts through the beam where you were showing the presence of the side lobes, where you said they might be compressed. That particular plot.
Yeah.
Cuts through the beam, multiple frequencies.
That one.
That one. Yeah, I'm curious, what are these tails on sort of the right side, positive theta y here, below the side lobe on the side? They're like a set of 6 lines that lie below the rest of them.
Yeah, let's see. I'm not sure what those are. So there were, it's probably an artifact of just data that should not have been included. This was done kind of quickly. So there was, this flight I think was not the full 2D grid. This was doing a cross pattern over the dishes. But there were also, just from the flight path, there were kind of like paths joining the tips of the crosses, so that the drone was like optimizing its its flight time.
Sure.
So this might be just like data that's not actually in the right place, but that's just included there. So it has much lower amplitude because it's farther away somewhere.
Gotcha. Just flying through a different part of the beam.
Yeah.
If I could ask a follow-up on, because of course HIRAX has a very redundant layout, and HERA is using this redundant calibration technique in addition to sky-based calibration.
Yep.
I was wondering if there's any goal to use redundant calibration for HIRAX or CHIME.
Yeah, there definitely is. So it's there are so John Sievers is kind of leading the software side calibration efforts, and he's working on kind of an extension to the usual redundant calibration methods that I forget. He calls it like pseudo redundant calibration or something. But there's the difficulty is that there's limitations to both of these methods. And so in the end, what will probably end up happening is that the full calibration product for the array will be a combination of many different methods. So the limitation to the redundant calibration is that it assumes that the array is perfectly redundant, which is never the case. There's always errors in the dish positionings or in their pointings, and there's like gain fluctuations and variations between elements, so it helps to have something where you're pointing a source at a single dish and measuring it to get a handle on those things. On the other hand, with the drone calibration, you're limited by just kind of like physical constraints of you've got this drone and it can fly for half an hour. But to map the full array of 1,000 dishes with any kind of precision would take just years of flight time, and so that will also just never happen. So it'll be a combination where we measure some subset of the dishes with the drone to very good accuracy, to get a handle on kind of the population statistics about how the beam varies and how gains vary, and then there'll also be some redundant calibration based off of sky sources or satellites. And there may also be some holography that people, which I didn't mention, but that is also work that's going on at Yale in South Africa.
Okay. Is there any other questions? We almost. Yeah, if there's no more questions, let's thank our speaker again.
Thank you.
Thank you, Ben. Very good.
Thank you.